Write each power series in closed form, meaning write it in sigma notation. Find the interval of convergence, being sure to test the endpoint separately, and then the radius of convergence. Okay, so closed form, sigma notation, I'm going to say take the sum. The signs are alternating, so I'm going to have a -1 to a power. I'm going to leave the power blank for the moment. And then every term has an x minus 1 to a power. I'm going to leave that blank. And then a denominator. Okay, so I should notice that I'm going to throw in a 1 in the exponent and in the denominator there. So notice that your exponent and your denominator always match. So 1, 1, 2, 2, 3, 3, 4, 4. So if I started at n equals 1, then my exponent on x minus 1 is n, and my denominator is n. So that would make my first exponent denominator pair be 1, and then 2, and then 3. Okay, so now I have to decide what exponent do I put on the -1. So I want my first term, my x minus 1 term, is positive. My first term is positive. So if I just put an n here, that would not work because that would give me -1 to the first, which would give me a negative first term. So I'm going to do n plus 1 on my -1. That way, when I plug in n equals 1, the exponent on the -1 is a 2, so my first term will be -1 squared, which is positive. Okay, so there's my closed form. Next step is to do the ratio test to find the interval of convergence. So the ratio test says take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So this is the limit as n goes to infinity of, I'm going to do a big absolute value here, and I'm going to put a sub n plus 1 on top. That means replace every single n in the closed form formula with an n plus 1. So this is -1 to the n plus 1 plus 1 times x minus 1 to the n plus 1 over n plus 1. And then in the denominator, I put the nth term, a sub n, which is exactly the formula that shows up in the closed form. So this is -1 to the n plus 1 times x minus 1 to the n over n. And then I'm going to do some simplifying inside that parenthesis. So this is the limit as n goes to infinity of the absolute value. The -1s actually don't matter at all because it's just going to end up being either -1 or 1, and I take the absolute value and it becomes 1. So I'm just going to stop writing -1s in here. And I'm going to have x minus 1 to the n plus 1 over n plus 1 times n over x minus 1 to the n. And simplify. So my x minus 1 to the n plus 1 over x minus 1 to the n, those are like bases that I'm dividing. So I'm going to subtract the exponents. And I get, copy the limit, n plus 1 minus n is 1. So I'm going to get an x minus 1 in the numerator, x minus 1, times n over n plus 1. Nothing there can cancel because there's no multiplication there. So n over n plus 1. If it was n over n times 1, they would cancel, but it's plus, so we can't do it. All right, so now I'm going to take the x minus 1 out of the limit because this limit only deals with n. So x minus 1 has no bearing on the limit, so I can take the x minus 1 out. I have to keep it in absolute value because it's in absolute value here, times the limit as n goes to infinity of n over n plus 1, and that limit is 1. So this is just the absolute value of x minus 1 times 1. And then to get convergence, the ratio test says that this limit that we're taking, it has to be less than 1. So I set that less than 1 and translate. That means that x minus 1 has to be trapped between 1 and -1. Add 1 to all three sides of this equation, and you get 0 is less than x is less than 2. So that is the open interval of convergence. All of the x's between 0 and 2 will make the power series converge. Now I have to check 0 and 2 separately. So I'm going to check x equals 0 and x equals 2. Let's see, I'll just draw some lines here. Okay, so x equals 0. If you plug x equals 0 into the original series, we get the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1. So I'm just going to scroll up so we can see the formula. I'm replacing this x right here with a 0. So I have times -1 to the n over n. Okay, so in my numerator, you're multiplying like bases, so you would add the exponents. So this becomes the sum from n equals 1 to infinity of -1 to the n plus 1 plus n is 2n plus 1 over n. Let's write out some terms. So if I plug in n equals 1, I get my exponent becomes a 3, and -1 cubed is -1 over 1. And then if I plug in n equals 2, my exponent is a 5, so I get -1 again in the numerator over 2. And if I plug in n equals 3, my denominator is a 3, and my numerator is -1 to the 7th, which is -1. And so this is going to keep going in this pattern, -1 to the 4th, plus -1, I'm sorry, -1 over 4, plus -1 fifth, plus blah, blah, blah. Okay, so that looks like the harmonic series. The signs are all negative. They're not alternating. The signs are all negative. So if I could factor out a -1, and I'd have 1 plus a half plus a third plus a fourth. And that 1 plus a half plus a third plus a fourth, that is a divergent p-series. It's a p-series where p equals 1. It's the harmonic series, which diverges. Okay, so for x equals 0, we're not going to include that endpoint. And then next I'm going to check x equals 2, the other endpoint here. So I checked 0. I'm not going to put an or equal sign right here, but I need to check the 2. So I'm going to plug in x equals 2. So this looks like the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1. If x is 2, 2 minus 1 is 1. So this is 1 to the n over n. And 1 to the n is always 1. So this is simpler, more simply written, -1 to the n plus 1 over n. And this is going to be an alternating harmonic series. If I plug in n equals 1, I get 1. If I plug in n equals 2, I get -1/2. If I plug in n equals 3, I get +1/3, then -1/4, plus 1/5. And this converges by the alternating series test. So I can put an or equal to sign on the 2 because it converges when x equals 2. So to finish writing this out, my closed form, I wrote this earlier, but I'll write it again in the answer line. This is the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1 to the n all over n. And my interval of convergence, we just decided, is 0 less than x less than or equal to 2. And the radius of convergence is the distance from the center of your interval to an endpoint. So sometimes it's helpful to draw this 0 to 2. That's my interval of convergence. not including the 0, but including the 2, which means the center of the interval is at 1, and the radius is 1. Okay, next one. Let's work on the closed form first. So this is going to be the sum. My signs are alternating, which means I'm probably going to use a -1 to a power. And then, so I've got some power I got to put there. Then I have x's to a power. So I'm going to have x to some power over a denominator. And it looks like the denominator matches the power in the numerator. So I'll leave that blank for now. Sort of just writing out a template. And then I want my first power to be a 1, and then I'm going to go 1, 3, 5, 7, odd powers. So a hint for how to write odd powers is 2n plus 1. So I'm going to put 2n plus 1 here and here, so that I have x to an odd power over that same odd power. But now if I plug in n equals 1, 2n plus 1 when n is 1 is 3. So this would be x cubed over 3, which is actually the second term in my series. So I'm going to fix that by starting n at 0 instead of at 1. So now if I plug in n equals 0, I have 2 times 0 plus 1 is 1. And that will be my exponent and my denominator, 1. All right, so now I have to figure out what exponent do I put on -1. So I want my first term to be positive. So if I start at 0, -1 to the 0 is +1. So I can just put an n there. And that will create the alternating signs that I want. Okay, so now I do the ratio test. I want to determine what x values will make this converge. So I take the limit as n goes to infinity of, replace every single n in the closed form formula with an n plus 1. So this becomes -1 to the n plus 1 times x to the 2 times n plus 1 plus 1. So replacing the n with an n plus 1 over 2 times n plus 1 plus 1. And then we divide by the nth term or multiply by its reciprocal. So this is 2n plus 1 over -1 to the n times x to the 2n plus 1. So with the ratio test, the -1 terms don't matter at all because they're either going to be -1 or 1, and I'm taking everything in absolute value. So I'm just going to stop writing the -1s here. So this is the limit as n goes to infinity. Okay, so I have x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over x to the 2n plus 1. The 2n plus 1 over 2n plus 3, nothing can be canceled there. So I'm going to leave that as 2n plus 1 over 2n plus 3. And then my x's, I'm dividing like bases. X to a power divided by x to another power. Dividing like bases, you subtract the exponents. So 2n plus 3 minus 2n plus 1 is 2. So I have an x squared in the numerator. So when I'm taking this limit as n goes to infinity, x squared is not affected at all by the limit of letting n go to infinity. So I'm going to take the absolute value of the x squared out of the limit and then just keep going with the limit as n goes to infinity of 2n plus 1 over 2n plus 3. And that limit is 1. So this just becomes the absolute value of x squared times 1. To get convergence, I have to make sure that this limit is less than 1. That's what the ratio test says. When that limit is less than 1, you get convergence. So to solve this, I have to sandwich x squared between 1 and -1. And this is sort of tricky to solve algebraically, so I gave you a graph to help you solve it. Here's -1, here's 1, and here's x squared. So I want to know, where is x squared between -1 and 1? Where is it sandwiched between -1 and 1? And it's all these values here. All these values on x squared are between -1 and 1. And that happens on this interval from -1 to 1 for the x's. So this is true when x is between 1 and -1. So that's my open interval of convergence. I have to test the endpoints separately. So I'll scroll up a bit to do that. So I think I'll rewrite my closed form so I can refer to it. N equals 0 to infinity, -1 to the n times x to the 2n plus 1 over 2n plus 1. Okay, so now I'm going to replace the x with a 1. We'll do 1 first. So this is the sum from n equals 0 to infinity of -1 to the n times x. X is 1, and 1 to any power is just 1. So this is times 1 over 2n plus 1. So if I plug in some values of n, so n equals 0 gives me 1. N equals 1 gives me -1 over 3. N equals 2 gives me 1 over 5, then minus a 7th plus blah, blah, blah. This converges by the alternating series test. The terms are decreasing towards 0, and the signs are alternating. All right, let's check -1. So this is the sum from n equals 0 to infinity of -1 to the n times -1 to the 2n plus 1. I'm replacing this x with a -1 this time, over 2n plus 1. Okay, in the numerator, I'm multiplying like bases, so I'm going to add the exponents. That becomes -1 to the 3n plus 1. 2n plus 1 plus n is 3n plus 1 over 2n plus 1. And we'll plug in some n values here. So if n is 0, I get -1 over 1. If n is 1, 3 times 1 is 3, plus 1 is 4, so this is +1. And that becomes 3. When n is 2, 3 times 2 is 6, plus 1 is 7, so I get a -1 in the numerator. And 2 times 2 is 4, plus 1 is 5, and then I'm going to get +1/7 minus blah, blah, blah. Okay, so this also converges by AST. Which means that my interval of convergence, I'm going to add some or equal to signs on the endpoints. -1 and 1 both lead to convergence. So let's write this all out. My closed form was the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. My interval of convergence, the ratio test said that x has to be between -1 and 1. And then we tested the endpoints separately and concluded that they both gave convergence. So I'm going to add some more equal to's. And then the radius of convergence is the distance from the center to an endpoint, which is 1 in this case. Okay, useful fact, 0 factorial equals 1. So I could rewrite this as x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, like that. And in closed form, that would be the sum from n equals 0 to infinity of x to the n over n factorial. So the ratio test says take the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial and divide by the nth term or multiply by its reciprocal, all in absolute value. So x to the n plus 1 over x to the n, that reduces to x. And then I have n factorial over n plus 1 factorial, and that simplifies to n plus 1 in the denominator. So this is x over n plus 1. I can take the x out of my limit. So this is the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. And this is the absolute value of x times 0, which is 0. Now, in order to get convergence, this limit has to be less than 1. So I have to decide what values of x make this limit less than 1. And the limit is 0 no matter what x is, right? That's always less than 1. So this converges for all values of x. It does not matter what x is. We'll always get a limit of 0, which is less than 1. So my interval of convergence is negative infinity to infinity, which makes the radius of convergence infinity. And my closed form, real quick again, n equals 0 to infinity of x to the n over n factorial. All right, so let's start by working on the closed form here. It looks like x minus 2 is in almost every term, and I could put it in this first term. It would be 1 times x minus 2 to the 0, because then it would go away. It would become a 1. There's no denominators. Okay, so then I have minus 1 times x minus 2 to the first. And then I have 2, 6, 24. That reminds me of my last problem. Right, I had 2, 6, 24. Those are factorials. So instead of writing this first one as a 1, I think I'm going to write it as a 0 factorial. 0 factorial. And then this next one I'll write as 1 factorial. And then this 2 I'm going to write as 2 factorial times x minus 2 squared. And then that 6 I'll write as 3 factorial. And then 24 is 4 factorial. So that's 4 factorial times x minus 2 to the 4th, etc. So now that I've written everything in terms of the factorials, I can write this in closed form a little bit easier. I'm going to start n at 0 because I have 0 in the factorial and the exponent. So this is n factorial times x minus 2 to the n. And the ratio test says take the limit as n goes to infinity of the n plus first term, so this is n plus 1 factorial times x minus 2 to the n plus 1 over the nth term, n factorial times x minus 2 to the n. Okay, n plus 1 factorial over n factorial simplifies to n plus 1. And x minus 2 to the n plus 1 over x minus 2 to the n simplifies to x minus 2 to the first. I can take the x minus 2 out of the limit in absolute value. Okay, now I have to make this be less than 1. This ratio I have to force to be less than 1. So let me write it again. This is the absolute value of x minus 2 times the limit as n goes to infinity of n plus 1. That is infinite. I need that to be less than 1. There's no way that can be less than 1 unless this term of my product is 0. So this can only happen if x minus 2 equals 0. Multiply that by anything. If this number is anything other than 0, multiply by a limit going to infinity, you're never going to be less than 1. So this only is less than 1 if x minus 2 is 0, which means x equals 2 is the only x value for which this converges. So we say the interval of convergence is just the set 2. The radius of convergence would be 0. There is no length there between the center of the interval and the endpoint of the interval. And then I'll rewrite the closed form here. It was the sum from n equals 0 to infinity of n factorial times x to the n. Oh, and it had an alternating sign. Right. To make the signs alternate, I need -1 to the n. Yep, that works. Okay, little mistake in my closed form. That's not just x to the n, it's x minus 2 to the n. Just rewrite that. So this is n factorial times x minus 2 to the n times -1 to the n.